All right, well, I want to add my thanks to the organizers and for the opportunity to make a little contribution to your anniversary celebration here. I understand it's a year-long series of meetings we're kicking off, and I hope this is the choice of this topic can remain and become a bigger part of the program here. I'd certainly follow it closely. Yeah, it's plugged in. It took a little while earlier. Let me just see. Let's try starting again. You should be looking at a photo of Ignacio Garzón, Professor Garzón. When we prepared this presentation, we first of all weren't sure of the diverse background of the audience, and secondly, how much we would you'd all learn from Thomas Björge's talk at the beginning. So I was making some adjustments to optimize the overlap or the complementarity of the two talks. So what I propose is to give the talk in three short stories, three short parts. One, kind of a background to complement what you heard in the opening lecture. So we could call that materials or molecules, the tangible stuff. The second part will be mathematics, or really measures. That's the key word. Well, one of the key words. And the third part will be models, mechanical models. And that'll be the inspirational part, at least I hope for the young people here, to see that you too can do chiral icosahedral symmetry in your spare time. And make the whole subject a lot less forbidding. So I'm going to go up to the general part, spend a couple minutes on this. Could we dim the lights because my contrast isn't as high as this is what I don't understand. There we go. Oh, source found, and it's gone. That's wonderful. So this is one man's take on chirality at the nanoscale, and that is that it's everywhere. I'm speaking from about 30 years of experience. And it tends to strike us as a surprising thing in clusters, atomic and molecular, metal, semiconductor clusters, because we're not looking for it. When we divide up a crystalline solid into very small units, let it rearrange to form its most stable, observed configuration, one of the last things we expect is for the surface, usually from the surface out inward, to reconstruct and expose an intrinsically chiral arrangement. And yet it happens again and again. I remember as a starter, faculty, UCLA with benzene clusters. You take them out of the crystal, a cluster of 13 benzene molecules, allow it to relax on a computer. You want to compare with the spectrum that you got. And it forms a pinwheel type arrangement of the molecules on the outside. And it's chiral. And it's not just a beginner. 20 years later, that's still the understood model. Water clusters, an assembly of 5 or 6 or 20 water molecules, take them out of the crystal structure, ice, let them form their optimal structure, take their spectra, do the theory on it. They form also pinwheel type structures. So it's everywhere. We all hear about the chiral fullerenes, perhaps, because they've been known for so long, the chiral nanotubes, different kinds of packing of tetrahedra, tetrahelix. And I'm going to talk more about this kind of packing of tetrahedra that you'll see in a structure like this. And I just want to offer an opinion on this. The cases where it really catches us by surprise, the thing that we're missing, if we're missing one general principle, it's that a symmetry lowering, a slight symmetry lowering to a chiral symmetry has the tendency to make the structures more compact. And when they're more compact, again, as a general rule, they're more cohesive. So at least at that level, we don't have to ask any further questions why chiral structures are preferred. We can, if we're mechanical thinking like that, we can say it's that. So to say it again, by going from a model structure that looks perfectly reasonable but is achiral, allowing it to relax, when it reconstructs, it becomes more compact by becoming chiral. And we see that again and again and again. So also in preparing this talk, it was pointed out to me by Professor Garzon, my colleague, that he attended a meeting in Europe with the same title a few years ago, and maybe it was a premature meeting because they didn't have a whole lot to say that you wouldn't have found in a good chemistry or biochemistry book. But I found this introductory article a little bit interesting. He said, chirality is an excellent subject for the application of symmetry principles. Chirality supported by point groups that comprise only proper rotations, namely C sub n, D sub n, O, T, and I. Now almost everyone knows the point groups, the rotation groups Cn and Dn, okay, uniaxial and triaxial. But these groups O, T, and I are a little bit more special, right, to most of us here. And he gives as an example right away in this a helicoil or helix type structure, and then shows a model for a viral capsid, virology. And points out that this has, to the best understanding of the structural virologists, the protein capsid on the viral, Icosahedral virus, are chiral. And that's indicated by these little symbols here. The chiral point group I, hence I metal cluster, chiral icosahedral is referred to by that symbol, okay, has the highest rotational symmetry based on 5-fold, 3-fold, and 2-fold rotation axes, multiples of each of these. And then there's a little description of this. But the last sentence caught my attention. It was so nice and concise. This example demonstrates how it is possible to construct a high symmetry chiral supramolecular structure from an association of low symmetry chiral macromolecules. And depending on your sophistication, and I'm very unsophisticated in these things, this may strike you as paradoxical or full of contradictions here. How can we take low symmetry objects and end up with rigorously high symmetry? Chiral icosahedral symmetry being very high symmetry, a group of order 60. Okay? And so this is what kind of the evidence tends to look like. These are some of my former colleagues that I pulled out for a talk recently at UCLA. And this one is not particularly strongly chiral. In fact, if you ignore the coloring scheme, it looks achiral. But once the coloring scheme to indicate the different capsid proteins of the viral capsid, once they're colored properly to indicate distinct, now we have something that's chiral. Of course, we need to inspect it all in 3D, but we go around in a circle and we can see that. Others are more profoundly chiral, even in their gross structure, even without looking at that scheme. But this is an example of what they're talking about. So we can ask the question, if it exists on the 20 nanometer scale, viruses, virons, does it exist in molecular structure? And the conventional answer is no, that the groups T, O, and I have never been found. Of course, chemists, molecular structure has higher standards of evidence. They want to see where all the atoms are. This I pulled from this chirality article 2008, and it says no, and they're quoting from the standard inorganic textbook. Molecules belonging to these groups are known. No example of its occurrence in nature is known, okay, has ever been studied. And I don't think these statements hold up anymore, even by the rigorous standards of structural chemists. Now, as Professor Bjerge mentioned earlier, we got our more recent start on this subject with gold clusters such as the gold 38 cluster. And this was the circular dichroism, or rather anisotropy factor spectrum. And the really interesting thing about this is that the glutathione ligand doesn't absorb anywhere in these regions, and even the gold glutathione polymer, non-metallic polymer, doesn't absorb in the near ultraviolet or in the visible. Well, somewhere in the near ultraviolet, but not at all in the visible. And here you have these very strong, all the way from the near infrared, all the way through the blue and violet. So the temptation is to say, well, this is the metallic part that is giving this strong optical activity. And so these bands were pulled out of gel electrophoresis. Those don't require any staining because the metals are so strongly colored. And you take them out and measure their circular dichroism spectrum. And one important question people always ask is, well, is it really the same cluster? Is it really the same structure when you have a chiral ligand like glutathione or you have an achiral ligand like hexane thiolate? And the answer, as far as the regular linear optical absorption, is yeah, it's the same thing, okay? And so it's not just that chirality has selected a different structure, and I think Professor Bjergi showed this. A strange experience going around in the nanochemistry and nanoscience world is many people ask, whatever made us think of doing circular dichroism on this? And I think that shows a deficiency in the education of a lot of chemists and certainly physicists. If you have a natural product, you use a natural product in a compound, as a ligand in a compound, then circular dichroism would be a standard thing that you do just to confirm that you really have that in the final product. Now here it doesn't work because the optical absorption of the metal clusters are so much stronger than that it dwarfs the contribution there. But I'm saying it should be kind of an automatic thing. So the more honest answer to why we did it is we were desperate for more information about the bands in the optical absorption spectrum. At least at that time, everyone said, well, these are just plasmonic blah bands of metal, colloids, and there's no more information hidden in them. They're just smeared out to the point you don't recognize them as nice plasmonic bands. But if their CD spectrum breaks that up into positive, negative going, and positive going, and negative going, all these transitions above zero, then they have to have their own character. And I would just say they're not completely understood even today, even though computational chemists have been let loose for years on this. So at a speculative level, at that point, we had already in the open literature, chiral metal wires, chiral cluster structures compared to their achiral ones. So you could do all kinds of speculations, but what's really changed in the decade since is the characterization, including crystallization, and the recognition of what is really involved in the structures of noble metals and ligands such as thiolates. So I want to emphasize that these are real materials, very strongly absorbing, crystallized, various forms, many different ways to look at them. They form ordered lattices. Thin optical films can be very, very strongly optically absorbing, and so on. And they can be handled nowadays by methods such as you handle a protein molecule of the same size. So you can do electrospray mass spectrometry. You can even couple it to liquid chromatography, HPLC. And you can separate out from mixtures the different sizes. You can prepare them in a raw mixture, in which case the electrospray mass spectrum shows you have 1, 2, 3 species in each of the different charge states. They show up. You treat them further, purify them further, and you end up with just mainly the one compound in the +1, +2, +3, +4 charge state. So the handling and characterization of these has developed to the point where it can really adapt to the facilities that you may have available standard in your institute. And the high resolution confirms all that, the 4 different charge states folded back up to unit mass. One of the ways of handling these further is to conjugate them, to couple them to biomolecules, but these could just as easily be synthetic macromolecules. And some of the schemes here are outlined in this methods in enzymology chapter. You can use the cysteine, the sulfhydryl group that's native in the proteins, or you can use various kinds of conjugation to do that. So that's pretty much my background, a few minutes, but I want to just say, what would we consider an ideal target for applications and further work? Might be something with about 145 or so metal atoms, 60 ligands, and it would have, at least to start with, this would all be gold or copper or silver. They tend to interchange pretty well without modifying the preferred composition. And the ligands might start out as something like these corannuline type units. So gray is carbon and blue is nitrogen right here. This is just a model. This thing doesn't exist yet synthetically, but there's no hydrogen, there's no oxygen, no sulfur, nothing else. But there's nothing wrong with the chemical bonding. That's the end road of a long series of things. So some of the applications of these, I mentioned the very strong optical absorption. They're a good match to the broadband or solar spectrum, so be good for light harvesting applications, kind of passive solar applications. You know, again, the absorption at 144 gold atoms is all the way from the near infrared to the blue violet, which is a very good match to where the important part of the solar spectrum. So we could talk about that sometime as you prefer. So now I'm coming to the measures, the mathematics, the chirality measures. And this is an unfortunately necessary topic. It's certainly not my favorite. It's my colleague Ignacio Garzón is on sabbatical leave in our place, but we've known him for about 25 or 30 years. So, and it's unfortunately necessary because people have very different impressions of whether the chirality is, to use their different words, intrinsic, extrinsic, profound, trivial, large, small, and all of that. So if we have a structure that we're unfamiliar with, I'm assuming you're unfamiliar with a gold 72 cage. It's very nice in many ways, depending on what's inside it. And you take its mirror image, as indicated by this journal cover image, and then you try to superimpose it, and you see that you can't. And you can go through the symmetry operations and see that, that indeed it's chiral icosahedral. There's still the question, is it really a large effect or is it a small effect? And I'm with the experimentalists who would say, well, let's just measure it, or at least calculate its optical, chiroptical, optical rotation, and all of that. But in the meantime, while we get around to measuring such a thing as that, everyone's arguing about it, and so it presents this problem that we need measures. And the measure that we're going to talk about is one of the most popular, most developed, the Hausdorff chirality measure. So this is the mathematics part. You can all take a break as you want. My colleague Garzón insisted that the best way to understand it is to go through this flow chart. So if you meet him somewhere, make sure and tell him, yeah, he went through this flow chart and it all made sense. Now we can skip that part and just say that the Hausdorff chirality measure is a measure of the overlap between two enantiomorphs or enantiomers, as you prefer, and that it has something to do with a distance measure called the Hausdorff measure. And it was introduced by Buda and Mislow and defended adamantly ever since. And Garzón brought it into the nano world, so to speak. So here's a definition borrowed from Wikipedia references and that describes it. And if you love mathematics, you'll enjoy this. You know, two subsets in a metric space, set. It's all set theory language. So I'd like to describe it in a few words without the use of any mathematics. I was going to do it with military things because I think that's where Hausdorff started. But coming up toward Canton and Youngstown, it became clear it had to be football, American football here. And so you want to measure how far apart two teams are on the football field. Here's what the Hausdorff measure does. It says find the most remote player on the field. Doesn't matter which team it is. It could be the free safety in an ordinary football play, all the way back there. Measure his distance, her distance, from the nearest player of the opposing team. That's it. That's the Hausdorff dimension. In another situation, a field extra point, it might be the kicker who's the farthest away from the nearest player of the other team, right? And of course, it's dynamic. It's changing when the teams are playing and they're intermingled. And someone, maybe the punter drops all the way back to be the safety there. He becomes the one from which the Hausdorff measure. So it's the proximity of the remotest player in the field. Now, if we replace those players in the field, each team, one team, by a molecular structure, all the coordinates of the structure, now we generate its enantiomer, its opposite enantiomer, L and D forms, and we try to superimpose it. It's that same measure. It's that same measure. I don't know if that was any good, but that's the best I could do on short notice. So here are some examples. This is the key slide of results, and many of these are new results. So what happens when we have an achiral structure, like icosahedral C60? It's 0. Here's palladium-145 from Wisconsin, Dahl's group. It's also 0. That's good because they're understood to be achiral. The others tend to be chiral, okay? And so you can look at these numbers, and they're 0.1, 0.1, 0.1, okay? There's some intermediate values in different places, but a lot of them max out around 0.2 and are as small as maybe 0.03, except in the case that they go all the way to 0. We're going to look at the structures that these were calculated from now. There's one more. The largest one he got just in the last week is the silver 132 shell. I'm pointing at the bottom here. The silver 132 shell on a copper cluster totaling 279 atoms, and that's 6.2%. So I'm going to try to refer to these as percentages. For example, if we take D2C76, try to imagine now generating its enantiomeric form, superimposing it as best you can using this distance measure to determine goodness of overlap. So get the best possible overlap. Now find the remotest possible of those 76 atoms of one enantiomorph from any of the atoms of the other enantiomorph. It is 10.9%. 10.9% of what? Of the diameter. 10.9% of the diameter. That's a big distance. 11% of this is the distance from the remotest possible atom of this one to an atom, not necessarily matched in any other way, to your enantiomorphic form. So, to me, that's big. That's profound. And the circular dichroism spectrum agrees. It's profound. It's up there in the 0.001, 3 times 0.001 anisotropy factor in the visible, across the visible, much of the visible range. So here's some structures to look at. You've heard of this one a lot already this morning. So gold-23, the ligand shell around that, hardly make out the color differences in the ambient light, but on this side you can probably. And so the core is only slightly chiral, 3% by this measure, and then it's 12% for the outer shell. So it's a little bit like you heard Thomas Bjerge explain already. It's the chiral patterning on the outside of the gold-23 cluster that makes up the gold-38 and gives it the final value for the chirality measure. Here's the historic first crystal structure from the Stanford group, Kornberg's group. The gold-79 core has very little measure, but it's not 0. It's about 2.8%. And by the time we have all the ligands on it with their chiral patterning, compact arrangement on the surface, we're up to about 1 part in 8, so 12.5%. See, it's not bad. When we only have one number to look at to express how chiral are you, it's not that bad. Here's an extreme case, gold-20 with some phosphorus containing ligands, phosphine ligands. There the number goes up to 1.7%, 16%. So that probably has some kind of profound helicity in it. Here's some bare clusters studied by electron diffraction in the gas phase, 12%. This one hasn't been studied experimentally, but it's about 9%. Here's the famous first determination of the 145 metal atom clusters. These are found all over the place, 144, 145 atoms with 60 ligands. And this one is considered achiral. You take the crystallographic data set and examine it, and sure enough, to 3 significant figures, it gives 0. But when you build a cluster to explain the ubiquitous gold 144 cluster, or any of its derivatives forms, you end up with a much larger number, 9%. So you want to break that down, and the core, the inner core of this, is icosahedral shell packing, but it's achiral. It's within the measurement of 0. You go to the outer layer of that, now you're up to about 3%. Okay, combining those two, you're at 3%. But there you're the same. But finally, putting the ligands on in the only way that they pack around that, you're up around 8.6%. So you're up near the very extreme value for chiral icosahedral symmetry Oh, I didn't write it there. Whoops, I'm going the wrong way. What am I doing wrong? Well, now you've seen everything. I lost it somewhere, but I think it's 10.1%. Yeah, we'll see it again. All right, so that was kind of a rapid fire tour through these recent results. And now, this was mentioned earlier this morning by Björgi, but the recent structure determination of gold-133 is the closest to determining the location of all the atoms in those chiral icosahedral clusters. It does have something that looks like a chiral icosahedral core, but then it really has a profoundly chiral, in fact D2 symmetry relation of all the ligands around here. And this is showing everything is gold in here except the different coloring scheme for where the sulfur atoms in the ligands. And this gives a very large number. Now, what am I doing wrong? I can only practice so much. Well, I don't have the number for it there, but it's the largest measured. All right, let's go to the third part, which is the you can do it. Does it say you can do it? Yeah, you can master chiral icosahedral symmetry. That's my next book title. I've never written a book, so it'll be the best one I've ever written. First of all, we need models we can understand, and I'm going to deal with a simpler one first where you can really see it. So a cube, you take a cube and truncate it. That means shave off the edges and corners, and you can come to this, which is used to teach crystallography all the time, and that's achiral. The way it can become a better 24 vertex, 24 ligands, 24 surface atom structure is the video here, which ends up at the most extreme chiral structure like this. And this thing, or something very close to it, is found, especially on the surface of semiconductor clusters. You get these 24 ligand structures like that. So if you watch this enough, it'll start to seem natural that some of the square faces become rhombuses, and do this. Okay? And by the way, these are both semi-regular solids. They're purely geometrical objects. It doesn't have to be chemistry or physics or biology here. Here's the chiral icosahedral transformation. 60 vertices. That's a lot of vertices to follow. Here again are the semi-regular polyhedra, which go by these cute little code names, as well as real names like snubdodecahedron, nicknames. 0% to 10.3%. And Thomas, you have every gradation from 0 to 10.3% as you undergo one of these these rotation operations. Okay. The rotation operations for the thiolate protected gold clusters are the staple formation, the pairing of the ligands force that, so it's quite intrinsic. So those models you could handle by hand. Here's a model that you can handle by hand, which has chiral icosahedral symmetry. In Southeast Asia, according to Fuller and Edmondson, children still play with a reed sphere consisting of 6 interwoven great circles. It's perhaps the oldest known football toy. Characterized by icosahedral symmetry, it's actually chiral icosahedral. It's virtually indestructible, and it has other good marketing properties. Lots of YouTube videos. So that's a regulation ball. It's not reeds, obviously. It's a synthetic polymer. To get it clear, Nishiyama in Osaka proposed that you make these things multicolored like this out of packing strap like that, and you can get a feel for how strong it is. Is it chiral? One way to tell is to make a right-handed and a left-handed and compare them. So we did that, and Nishiyama confirmed that too, that yeah, you can make right-handed and left-handed ones. And the ones that indicate where the ligands are in the chiral icosahedral clusters, we marked with little dots like this, and that's a right-handed and a left-handed version. They're tied together to keep them together. So I've seen high school students make these, graduate students, again, in their spare time. This is what they look like on Texas grass, with the thing, the left and right-handed one like this. If that's not enough, you can always go to a modern geometry textbook. I recommend Conway's Symmetry of Things book. And on any number of pages, you'll find that chiral icosahedral symmetry is real. Some exotic sculptures, origami, the polyhedra mentioned already. And you can compare full icosahedral with chiral icosahedral symmetry. I like this one a lot because the snail's photo that you had earlier. And notice the really interesting part is when you go from chiral icosahedral to achiral icosahedral, now you have double the number of the snails. This is a group of order 120, which is truly huge to have 120 symmetry equivalent ligands or atoms. This is a group of only order 60. But you've gained an enormous benefit. You've compressed, you've compacted it, and you've introduced chirality, a chirality that we would argue is a profound chirality, not a trivial or you can hardly see it kind of thing. What you probably can't see is that the structure becomes that much more compact, but that becomes clear when you examine the models that it's compressed by a fair amount. All right, here's a challenge that hasn't been met. Why is there no standard inflated ball that's chiral icosahedral? This thing has been made, but that's the achiral partner to it. So that would be a good challenge for someone with an inventive mind is to make that and characterize it. So I don't know how I'm doing on time. I have a session here.
We're getting close to the end.
All right. I could go a lot further, but I think this is a good point to sum up. We show that the Hausdorff chirality measures are comparable to those of other profoundly chiral, like chiral fullerenes. We compared also to these standard polyhedra, the 133 and the 145 structures. I didn't say anything about extending these to larger shells other than pointing to that 132 atom shell. But these things are in the literature. You can see all these examples of compactifying an icosahedral shell by this kind of strange rotation. So I don't think you'll be able to escape it, you young people in your life. It's everywhere out there. You'll come across it. Okay, thank you very much for your attention.
There's time for one or two quick questions. Randy?
I had a question. You showed the C72. He said 10% for that too, right?
Yeah.
He said, that's weird because it doesn't look like that. But I was thinking about like limonene.
Sorry, limonene?
Limonene, okay. Right? I mean, limonene, usually you can say, oh, your nose can smell a proton moving a nanometer, which is pretty cool, or an angstrom. But the molecule isn't that big. Wouldn't that be 10% also? Even for, the dumb little chiral molecules?
Okay, let's get the coordinates. And
I know they smell different. I'm asking if the number's 10%. Slightly related, so Peter talked about this. Okay, they talked about gamma, right? That pseudoscalar, that's a number with a sign. And all these measurements are without a sign. So how does it tell you which sign to assign to which enantiomer?
Well, remember, the definition has both enantiomers in it
Right.
and superimposed. So no, it doesn't give you any of this additional.
So how would Peter take your information?
Well, we should ask Peter.
Okay.
One last question.
Okay, I can make this structure, this icosahedral thing, out of those little magnetic beads.
Yes.
The shape has no chirality to it, but if you look at the magnetic moments, they define a chirality because the north-south chains go clockwise or counterclockwise relative to the bowl shape of each little piece of it. So the chirality is there, but it's not in the shape. That Hausdorff measure is not going to catch it.
It won't catch it at all.
Yeah, but does that exist in the molecular world?
I don't know.
Well,
That's a good
dipole,
question.
magnetic dipole moments can, I guess it's not just shape, there's other properties
Right.
that can impose chirality.
Right. So turn those subunits into little little dipoles.
I also recommend you look at something called IQ lights. Those are little pieces that you can fit together into a variety of chiral shapes. you probably would like to
Super.
decorate your lab with them.
Yeah, thank you.
Very good. Thank you.